All right, part two of Pendulum Notes is a look at forces, which in this case unfortunately means torque. So if we draw a free body diagram of our pendulum bob, which remember we put it on a string, let's do blue here. We put it on a string of length L, and I also said choose the pendulum bob that is really heavy. So this guy needs to be much heavier than the string. So for a simple pendulum, which is what you guys use during the lab, so simple pendulum, mass of the ball is much greater than mass of the string. And we really want to do this because for a simple pendulum, we want the rotational inertia of the whole thing to be all of the mass on the end of the string, and the string basically doesn't matter. The result is the rotational inertia is ml squared. Now let's draw a free body diagram of this guy. So we have our ball, and we have initially tension is at an angle, and the weight is straight down. Now let's extend this guy down here, and here's our theta. And what I want to do is, instead of splitting tension up into x and y pieces, let's change the direction of x and y so that tension is along the y-axis and the x-axis is the initial direction of motion of the pendulum bob. And what that means is that our mg is going to be off the axis. So this guy, whoops, didn't label my mg here. So mg is off the axis, with the result that this piece right here, mg sine theta, is the part of the motion that causes it to rotate, to swing back towards equilibrium. And this cosine piece just balances the tension and keeps the string tight so that it's not all floppy. We don't really care about that right now because that's not doing anything interesting. This is the guy that does the interesting thing. So let's take a look at the effect of these torques on the motion of the pendulum bob. So remember, torque is R cross F, and what it produces is a twist about some axis of motion. So the axis of motion is way up there at our ceiling, or for you guys during the lab, the clamp. So that guy, it's right there, that's the pivot. Now, our radial length is from the pivot all the way down to the center mass of the bob, which is why during the lab I said you need to make sure that you measure from the bottom of the clamp down to the middle of the pendulum bob. Now the force is going to be this mg sine theta. Tension points along the string, so there's no crossing going on there. And mg cosine theta also points along the string, so there's no crossing going on there. So mg sine theta is the part of the force that is perpendicular, and we need to add in a detail here, the fact that it drags it back towards equilibrium. So since it's pointing back towards equilibrium, we need a minus sign. So let's label that guy points toward equilibrium. let's fill in our details here. So r turns into the length of the string, and it's already perpendicular to, so L points up and to the right, and mg sine theta points down and to the right, and they're going to be perpendicular. So we don't need that cross anymore. We've taken care of that. And there's a minus sign from the mg sine theta, and then we'll have mg sine theta here. And on the other side, we will have, for a simple pendulum, this is ml squared, so we will have ml squared, and then alpha. Now, we can cancel a few things out here. So we can cancel out one of those L's. Here, I'll use red. We can cancel out one of those L's and an M and an M and an L. And that leaves us with minus g sine theta equals L alpha. Now let's take a look back over here at our kinematic equation that I wrote down to remember alpha equals minus omega squared theta. Well, I have an alpha here, and I have a minus sign, and I have a couple of constants, because remember, omega is a constant. It's 2 pi over the period, and the period is just how long does it take to go over and back again. So g and L, those are two constants, but we have a problem here with this sine theta thing. So we need to get rid of that somehow. Well, we're going to use some calculus to get rid of that. And here, let's switch to, I'll use black for this guy. All right, so sidebar. There's a thing in calculus, well, you don't get to it till you get to calculus. I shouldn't really say that it is in calculus, but it's a, that's embarrassing. It's not Taylor, it's Taylor. If you're in BC Calc, Snow tells me that he's already introduced this to you, and it's called Taylor series, after some dude named Taylor. Unless he introduced it to you as Maclaurin series, after some other dude named Maclaurin. Now the idea is you can approximate almost any, I'll just say any function, and we'll use time. He probably used x. Well, we'll use theta here because we're getting rid of theta. So let's do theta. Approximate any function as a polynomial. With a series of derivatives. Now I could show you the formula for that, but it doesn't really matter, that general formula. So I'll just show you the formula for the sine. For the sine function, sine theta, it's approximated as theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial plus, and so on and so forth. The exponents go up by the odd numbers, and the factorials also go up by the same odd numbers. Now, how are we going to get rid of sine theta and turn it into this thing? Making it any better doesn't make any sense to me until you say, here are the following conditions. Small angles only. Well, what does that do? Well, let's do sine of pi over 6. Sine of pi over 6, which by the way is 30 degrees, gets you 0.5. Well, what is pi over 6? Pull out your calculator and you get 0.52. Those are pretty close together already. That's only a 4% difference. That's 4%. So if we say instead of doing sine of pi over 6, I'll just plug into my calculator pi over 6 and treat it like it's the same thing, I'm off by 4%. Well, what if I do sine of pi over 12? Instead of 30 degrees, let's do 15 degrees. Well, sine of pi over 12 and pi over 12, they're both about 0.25. And the difference is in the third place, which makes the error a lot less than 4%. So for those of you who pulled your pendulum way back up and let it swing, and then were timing it, and I said, no, don't do that, here's why. What I want to do is make an approximation here to get rid of that sine function and replace it with just the angle. So let's take a look at this formula over here, this polynomial. Let's take a small number, raise it to the 7th power, and then divide by 7 factorial. Well, 7 times 6 times 5 times 4 times 3 times 2 times 1 gets to be a pretty big number. So a small number to the 7th power is really small. Divided by a big number, it gets even smaller. So we can ignore that. How about to the 5th? Same deal. How about to the 3rd? Well, as long as you keep your angle small, theta cubed is going to be even smaller, and then we divide it by 6 again. So we can cancel that guy out and ignore that as well. Therefore, for a small angle, we can approximate sine theta as theta. And that is called the small angle approximation. We're going to use this up here, and we're going to get rid of theta. We're going to get rid of sine theta and replace it with theta. Okay, end sidebar, and now I need that space back. I wonder if there's a faster way to delete this stuff. It's been a while since I've used this wireless slate. What if I do this? Yeah, let's just delete. Yeah, you, and you, and you, you, you. You all gotta go. And oh, come on. You. Okay. At this point, I'll just do this. All right. Now, using the small angle approximation, small angle approx, we're going to get minus g theta equals L alpha. Okay, now we can do this guy. Let's get rid of alpha and replace it with minus omega squared theta. So minus g theta equals L times minus omega squared theta. And now we can get rid of that pesky theta thing. And we can also get rid of that minus sign. And by the way, omega equals 2 pi over the period, which is what we're looking for anyway, and that's what I had you guys measure during lab. You measure the period. You didn't measure the omega, you measure the period. So let's get our equation that we can then use in terms of the period. So let's see here. This guy will be, let's go back to blue. This guy will be G over L equals omega squared equals 4 pi squared over t squared. And then when we rearrange this guy, cross multiply and put the t squared up here, and then the L and the G over there, and then we take the square root, we end up with a very useful equation, 2 pi square root L over G. This is something that is worth memorizing, and you will have an assignment for it at some point.